Chemistry. We are moving on to the answers video for the day 32 lesson. This is Basic Gas Laws 2. This does include some math type of problems, so I'll do some of those with you here. So down here we have a graphic organizer that looks very much like the one that you've seen for day 18, 19, where you go grams to moles, moles to grams, you go across. Okay, I've added here the molar masses. I didn't include those on your sheet, but you know how to compute those by now. The one thing this adds is this relationship that 1 mole of any gas equals 22.4 liters. So you don't care what the gas is. And that's at standard temperature pressure, and that's the only circumstance we're going to deal with at this level. And standard temperature pressure, the standard pressure is 1 atmosphere. That's the pressure you feel here at sea level. And 0 degrees centigrade, that's the freezing point of water, which for a gas is not really all that cold. So that's not as though, unless you're dealing with water, which could be frozen. But anyway, you kind of ignore that concept here. Okay, so what we're going to do is just go ahead and jump into these using this graphic organizer right here. So first question is, how many grams of C3H6O are required to create 6.4 liters of CO2 gas at STP? So we come over here, grams of C3H6O, it's how many, so there's the question mark, and it wants to know liters of CO2. And it's it starts with 6.4 liters of CO2. So you come to CO2 and you go up to the liters column, or the liters row up here, and that's 6.4. Okay, so what's your path? You're going to come down into the equation using this conversion. Now it's 1 mole of, and it says H2. That was from a previous lesson that I didn't change. You can scratch all of those out. It's any gas. 1 mole of any gas equals 22.4 liters. So just scratch out all the H2s. It doesn't matter what gas you're dealing with. So 6.4, you use this conversion to get to here. And now you need to get from here to here. How do you do that? You use what's in the chemical equation. That sets up your equivalency to go across the chemical equation. So it's 1 C3H6O equals 3 CO2. And those are moles. And then once you get to here, you come out using the molar mass, which you can figure out of C3H6O. All right, so let's go ahead and set this up. Okay, this is what I'm looking for, grams of C3H6O, and this is what I'm starting with, 6.4. And we saw it's going to take 3 conversions. Boxes are optional, but the number of conversions is going to be 3. Okay, first equivalency is the one we said. 1 mole equals 22.4 liters for any gas. Okay, so now we are sitting in this box right here. Now we need to move across from here. So it's 1 mole C3H6O equals 3 moles CO2. Okay, now we're sitting in the box of moles of C3H6O, and we need to use the molar mass to get us to our final answer of grams. Okay, and we multiply everything on top and divide by everything on the bottom. And we are left with 55.3 grams. And that's our final answer. Okay? All right, let's do let's do C. I think you know how to do moles to moles and grams to mole because that was day 18 and 19. So let's go on to C. Let's just do the ones that deal with liters. So we're going to come over here. And the question is, for C, we're doing C, how many liters H2O? So you come up here, it's trying to find out number of liters, so that's our question mark. Can be produced from 2.25, that should be 2.25 decimal point grams of O2. So come down to O2 and it's 2.25 right there. So our path is to go up through the molar mass of oxygen, from oxygen over to water using the equation, this equals this, and then coming out using 1 mole of H2O equals 22.4 liters of H2O, because this is true for any gas. All right, so let's go ahead and write this out. And it's 3 conversions. Okay, first conversion first equivalency is the molar mass of oxygen. Is the molar mass of oxygen right there. Okay, so now we are in this box right here in moles of O2, and the equivalency is 4 moles of O2 equals 3 moles of H2O. Okay, and again, remember, the only time you use these coefficients in front of the substances is when you're going sideways. You never use them going up and down. Molar masses are always 1 mole, 1 mole. Even these up here are always 1 mole, 1 mole, 1 mole. Okay, so the 4 and the 3 are only used when you're going side to side. Okay. And finally, we're sitting in this box, and we have 1 mole of H2O equals 22.4 liters of H2O. And now multiply everything on top, divide by everything on the bottom. And we get 1.18 liters of H2O for our final answer. Okay, so you can pick up from the rest of these. I'm going to cross this one out. This was a question that I decided to delete. We're going to leave that. And we're going to move on to the next question. There is a correction to make in this one. Okay, and I'm going to move down here to letter D, and it should be Li2CO3. Other than that, I don't think there's any issues. Okay, I've done several grams to liters. Let's do a liters to liters. Let's do C. So I'm going to come down here and do C. How many liters of H2O are formed if 89.7 liters of CO2 are completely reacted? Okay, so we're going to come up here. First of all, we need a couple of molar masses up here, so let's compute those. You can do that on your own. Lithium is 6.94, oxygen is 16, and hydrogen is 1.01, and you have one of those. Remember, when you compute your molar mass, it's always 1 mole. Don't get confused by the coefficients in front of the equation. Okay, so I've gone ahead and added the molar masses for each of these substances. You're not going to need them on this question, though, because it's asking how many liters of H2O. So we come up here. We're trying to find liters of H2O way up there on the top right. And then it says are formed if 89.7 liters of CO2 are completely reacted. So the 89.7 is going to go up here above the CO2 because it's liters, so it has to go up in the liters row. So our path is to come down using this conversion to get to moles of CO2. Then we go across to get moles of H2O. And it's 1 mole of CO2 equals 1 mole of H2O. So that makes that easy. And then you come out using this conversion to finally get the liters of H2O. So let's go ahead and set this up. And we can see that's 3 conversions. First conversion is the CO2, 1 mole equals 22.4 liters. Just add the substance, and again, scratch the H2s. That's an old problem set. Okay, so 1 mole CO2 equals 22.4 liters of CO2. Okay, and that puts us in the box right here. Now it's just 1 mole CO2 equals 1 mole H2O. Okay, that puts us in the moles of H2O box, and now we need to use the standard conversion again, except for H2O, to get us out into our final answer. Okay, now we multiply everything on top, divide by everything on the bottom. Okay, and what we get is 89.7 liters. Same thing we started off with. Why is that? Is that just a coincidence? No, it happens that the conversions to get from moles to liters of any gas is the same, so those two numbers are the same. And we happen to have a 1-to-1. 1 CO2 equals 1 H2O. So what you ended up here was 89.7 liters of H2O, the same number of liters that you started with of CO2. That won't always happen, but that's how you do a liters to liters. Okay, I made this correction here already. This one, you're going from grams to liters. We did 2 of those already on the previous problem, so I'm going to leave the rest of them up to you. Okay, and we're going to move on to some other problems in this problem set. Okay, so we're on to number 2. This one was actually done in the lectures video. I'm going to go ahead and do it again here because it's just a concept question to be sure you understand that at STP, 1 mole of any gas produces 22.4 liters of that gas, as long as you're at STP. And let's write down just... Okay, so STP is 1 atmosphere and 0 degrees centigrade, or in Kelvin, it's 273 Kelvin. So what we're going to do is use PV equals nRT. Okay, and we're going to solve for volume. We want to see if we put 1 mole into N, do we get a volume of 22.4? So we're going to divide both sides by P. This is just algebra. And that gives us the following equation, that the volume equals let's define our terms in this case. We're dealing with 1 mole. We want to see that 1 mole produces that. Okay, again, you get 273 from centigrade. Centigrade plus 273 equals Kelvin. So 0 degrees centigrade plus 273 gives you that. Pressure's 1 atmosphere. That's standard temperature pressure, and it has to be in atmospheres. Again, what this tells you, this gas constant tells you is, it tells you what units you have to be in. So for volume, you have to be in liters. Well, we're looking for volume, so that means our volume is going to come out in liters. Atmospheres for pressure, moles, it's just moles, number of moles, and the temperature has to be in kelvins, okay? So we're going to plug in these numbers down here. Okay, so there's all our substitutions. Now, let's see our unit cancellation. We're going to actually practice that down here in the next problem, but let's see. So this was in the lecture video. So this, if it's only on one level, it's on the top. So this is the numerator fraction, this is the denominator fraction. So it's moles on top, that's numerator top, can cancel with numerator bottom. Numerator top here, Kelvin cancels with numerator bottom, Kelvin there. Atmosphere is numerator top, and atmosphere down here is denominator top, so they have the word top in common. Again, this was all in the lecture video. And so the only unit you have left is liters, and that's what you want for your final answer. You want volume to be in liters. So when we go ahead and do that calculation, we get volume equals 22.4 liters. So that means the volume of any gas. And how do we know it's any gas? Because it doesn't specify anything in here about what gas it is in this equation. It doesn't ask for the molar mass. It doesn't ask for anything that would be a characteristic of a specific gas. So 1 mole of any gas equals 22.4 liters. And that's if you have the temperature at 0 degrees centigrade or 273 Kelvin and pressure at 1 atmosphere, standard temperature and pressure, those two, okay? All right, let's go down and do one of those and really practice. Now, we did this one in class. If you didn't see it, then you'll get to do this one on your own. I'm going to do this one. This is a little bit harder one. So what we do is we remember the top is the numerator fraction, the bottom is the denominator fraction, and we're going to refer to this, the very top, as the numerator top. Refer to this as the numerator bottom, denominator top, and denominator bottom. Okay, so remember, if they have any two words in common, any word in common rather, they can be canceled. So numerator top can cancel with numerator bottom because they have the word numerator in common, and the word numerator top can cancel with denominator and top because they have the word top in common. Numerator top cannot cancel with denominator bottom because they don't have either of any of the words in common. Okay, so the way I would do this one is I'd break all these squares out into individual units. So here we go. So what I did was broke mole squared, which is moles times moles, into that, moles times moles. I broke Kelvin squared into Kelvin times Kelvin, so this is the numerator fraction. Now we go to the bottom. Okay, so again, all these, in between these are time signs. I think you all know that. You're multiplying everything here, multiplying everything here, everything here, everything here. Okay, so let's go ahead. You can just start canceling anything you want that fits. So numerator top, numerator bottom, numerator top, numerator bottom, numerator top, numerator bottom. Okay, and now we have numerator top, denominator top right there. And we have numerator bottom, denominator bottom right there. So we've taken care of everything here. And let's see, we don't have any more moles. So the only thing left is that. And then everything you see here. No, not true. Atmosphere and atmosphere. That's denominator top, denominator bottom. They have the word denominator in common. Atmosphere, atmosphere. Same thing for those two. Okay, so that's gone. Liters, we got a liter there, and that's denominator top, denominator bottom. That's gone. And we have no K's left. We have no L's left to cancel. We have that one atmosphere left. So this is going to be, I got to figure out where to write this. I'm going to come up here and write this. So all of this up here is just moles. And I like to put the 1 on the bottom. So this is the numerator fraction because everything in the numerator bottom canceled. Okay, then I'm going to come here. And all we have here is atmospheres and grams. Okay. And what we have on the bottom is liters and Kelvin, Kelvin, Kelvin. But now we can put those together, liters and liters. We're going to put it back and make it liters squared again. And Kelvin, 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 we're going to make it Kelvin to the third again. So there you go. Okay, and I'm going to need more space. I'm going to move up here again. And you flip the bottom and multiply. So over here you have mole. And you flip the bottom here. So it's L squared, K squared, K to the third, over, and then this goes on the bottom, ATM. You simply flip this over. Okay, and what you get, again, I keep running out of space here, but what you get is moles, liter squared, Kelvin squared over atmosphere. That's your final answer, okay? You leave it like that, I don't care, but you really should put them together. And that's that. That's a tricky one. You're never going to see anything like this in chemistry. This is like it's like a drill. It's like an exercise to learn the rules of unit cancellation. Now this one's easier. This is the one we did in class. I'm not going to do this one. You can do this one. Okay, here we go. An unknown gas contains 3.42 grams in a 14.2 liter container. What is the density of the gas? Okay, so density is simply mass over volume. So write the formula and you'll end up memorizing it. It's mass over volume. Mass is measured in grams, volume is measured in liters. So very simply, it's 3.42 grams over 14.2 liters. The final unit of measure is going to be grams per liter, and so you do the math on that and you'll be done. Okay? An unknown gas has a density of 0.81 grams per liter at a temperature of 298, that's 25 degrees centigrade, 298 Kelvin, and pressure of 1.1 atmosphere. The ideal gas constant is liter atmospheres moles Kelvin. What is the molar mass of the gas, and what substance do you think it might be? Okay, so molar mass, and the silly little mnemonic I learned for that once is molar mass kitty kicks dirt over pee. Okay, so when a kitty goes pee pee, it puts dirt over it, right? So it's dirt over pee. Now you can plug in the numbers, the gas constant, temperature 298, it has to be in Kelvin because the gas constant is, and the pressure is 1.1 atmosphere. First of all, be sure your units cancel. So numerator top, denominator top, numerator top, numerator bottom. Liters is numerator top and numerator bottom right there. And your final units are grams per mole, and that's molar mass. Molar mass is some number of grams per mole. Okay, for water it's 18.02 grams per mole of water, okay? So do the math on this. And what we get is 18.02 grams per mole. So what substance do you think that could be? Well, I just gave it away. It's probably water, okay? That's 18.02 grams per mole. All right, move on. A mixture of air contains 0.78 moles of O2, 0.22 moles of N2. That's reasonably close to the real numbers. The pressure of the air is 1.05 atmospheres. What is the parcel pressure of the O2 and the N2? So you use the mole fraction. So here it is. To find the pressure of the O2, that's going to equal the total pressure, which is 1.05 atmospheres, times the mole fraction for O2. So what is that? It's going to be, everything's in moles, so you don't have to convert anything from grams. So we take this and divide it by these two added together, which is going to give you 1, and multiply that by 1.05. And that gives us 0.819, and it is in atmospheres, because it tells us right there that we're using atmospheres. Okay, let's do it for nitrogen. And that's atmospheres, and that's for N2. And what would you get if you added those two together? You get 1.05, the total pressure that you started with. Okay, so you can check your work by doing that. Okay, this one is the same, 7. You do it the same way. You use a mole fraction of each, and then the total pressure is given to you, this time in torr. That doesn't matter, just means your final answer is going to be in torr rather than atmospheres. You don't have to convert. Okay, there's no reason to convert to atmospheres in this. Okay, number 8, what are the 4 tenets of kinetic molecular theory? That's straight out of the video. You just write them down, list them, and then know them for a test. Okay, compute the molar mass of HCCO2 and then use Graham's law of effusion. We've already done this one a couple times. Let's just do it. HE, you can get that off the periodic table, is 4 grams per mole. And CO2 we've done 1,000,000 times. So we want the bigger one on top, so it's the square root of the heavier over the lighter, and just do the calculation, do the division, and take the square root of that number. Okay, and I'm going to show you how to do this on the TI-30 because it's a little quirky. If you want to do that, you have to first put in the square root function first. So it's second, and then the x squared button, but that gives you the square root up above. There, you see it. Now you do 44.01 divided by 4 for helium, close the parenthesis and hit equal, and you get 3.3. That's good enough. So what does that mean? I want you to write out what it means. It means the lighter, which is the helium moves 3.3 times faster than CO2. So if CO2 is moving 100 meters per second, the helium will be moving 330 meters per second. If the CO2 is moving 10 meters per second, then the helium will be moving 33 meters per second. Okay, so it's a relative speed. It just means that helium's 3 times faster. Okay, 10 you can do on your own. Okay, number 11, the formula. This formula gives the absolute speed of a particle in meters per second. So now you're not just giving a relative speed that Graham's law gives you. You're actually giving the actual speed in meters per second. So what is the average speed of a helium at 300 Kelvin? So the formula here is 3R gas constant times T over the molar mass. Okay, so the molar mass, let's write down what we have. The molar mass for helium grams per mole, and the temperature here they gave us is 300 Kelvin. Now, there's a little trick here. This is a different value of the gas constant. Notice that it has joules on the top instead of liter atmospheres. Moles Kelvin is still the same on the bottom. So in other words, this is equal to the one we've been using. Okay, they just did a conversion where they got to joules, which is the standard unit of measure for energy, over moles Kelvin. So sometimes this is the gas constant needed if you're working with an equation that uses joules rather than liters and atmospheres. But just keep in mind that these two are equal to each other, okay? Liters atmosphere becomes joules, but the number also changes when you do that, okay? So that's going to be our gas constant R. So here we go. We're going to plug in. And U is used in chemistry for meaning the speed here. So here we go. And the 3 has no units to it. It's just a number that's part of the equation. Okay, so the units are going to be a little odd here. You have moles in the numerator bottom and in the denominator bottom, so they cancel. And then on the top, Kelvin, numerator top, numerator bottom. Okay, now I'd have to break down joules into its constituent units to get how this gives you meters per second. I'm not going to do that. Just trust the equation that it will give you, as long as you set the units up properly and the numbers, it will give you meters per second. So I'm just going to do the calculation here. Okay, again, I'll show you how to do this. You got to put up the square root first, so it's second x squared. That brings up the square root symbol. You can, whoops, let me get the calculator on. Second x squared, that brings up the square root symbol. Now we're going to put all those numbers inside of it. 3 times 8.314 times 300 divided by 4 equal, and then you close the parenthesis and you get 43.25, 43.3. meters per second. Okay, so that's your final answer. So you have one to do on the next page, and I'll leave that one for you. There it is right there. And then 13 and 14 are concepts, just definitions straight out of the lecture video, so watch those. Same with that. What is van der Waals equation? What is the purpose of it? I'm not going to ask you to compute anything with van der Waals equation, just what does it do? Alright, and that takes care of this answers video.